Okay, so we'll get started. So good evening, everyone, and welcome to SciSoc's second talk of this year. It's our great pleasure to introduce our speaker today, Professor Gábor Csányi, from the Department of Engineering at the University of Cambridge. Professor Csányi has had an illustrious career across multiple fields in academia and is a leading figure in the intersection of physics, chemistry, and AI. He first read mathematics for his undergraduate degree here in Cambridge, followed by a PhD in physics at MIT, and has gone on to produce groundbreaking work in computational chemistry via the applications of machine learning to molecular modeling. Professor Csányi has won the F.W. Bessel Award of the Alexander von Humboldt Foundation for his work, and was also recently elected the Fellow of the Royal Society for his contributions. Please join us in welcoming Professor Gábor Csányi to share with us how machine learning forces fields show extreme generalization. Professor Csányi, please.
Okay, can you hear me? Okay, good. Okay, thanks very much for the invitation. It's a pleasure. It's always a pleasure to talk to students and to enthuse about what we do. Just over the road. So my lab is in the engineering department. As Jeffrey said, it's just across Trumpington Street. Okay, so let me start by showing you one of these. I want you to think about the length scales of the material world. So I'm going to start with one of these length scale videos. Let's see if that's okay. So you see the whole thing, and if I do this, okay, you see it. Okay, so we're zooming in. Okay, so just get you into the mood of thinking about a material that's on a human scale, and we go in and you see the surface. Of course, they're going to switch technique, microscopy technique in between. That's what the smooth metal looks like when you zoom in. And then you zoom in some more, and now you start to see rows of atoms. And then there's a change in technique, and you see an atom. And then for a long while, you don't see anything. It's a big jump in length scale. And then you see the atomic nucleus. And then inside it, well, that's not a microscope image. That's just someone's fantasy. Okay? But that's the length scales that are all below us is what's shown here. So go back to the presentation. And so I want you to think about understanding the chemistry and physics, the world, the material world, on these various different length scales. So we have what I termed here the device scale. So the device could be that pen, or in this case, it's a bridge, right? And the components of a bridge are, if I want to model it, if I want to understand how it works, it has components, and those components are the various beams and trusses and cables that hold up that bridge. And the properties of those components and how they interact together, the properties of the device, is actually mostly done by simulation. Right? You don't really want to build a bridge to figure out whether it will break or not. People used to do that, and there was a lot of accidents. And now we can actually simulate all of that. And when things do go wrong, like with the Millennium Bridge in London in 2000, well, that's because they didn't do enough simulation. And when they went back and did it again, okay, they missed out a few things. But we could actually understand how devices work. And it's classic, in the case of bridges, it's classical mechanics. Then you go down to the object scale. So they would say one of these beams and trusses and cables. What are the components of that? Well, it's materials, right? So metals, plastic, wood, the piece of metal in the pen. And when you think about the properties of materials, actually the best way to assess those currently is measurement. We can take those materials into the lab, we can cut a piece, go into the lab, and measure the properties that we want to know, that we need to know in order to do the higher length scale simulations. And there's a field that deals with this. It's called solid mechanics, and it usually deals with describes the empirical laws that connect those experimental data. And then below that, we could call that the material scale, So when I want to understand how a certain material works, again, there are components. But what would the components be? So that's much less obvious now. In case of solid materials or metals, it will be crystals, right? So the arrangements of atoms in sort of neat planes next to one another. So in case of plastics, it will be fibers of that plastic. And these properties are also established typically through measurement, mostly. And again, solid mechanics is the field. If you go one further down, then what is a crystal made of? It's typically atoms, right? Atoms form crystals. Molecules make the fibers of the plastic. And now the properties are established by a combination of simulation and experiment. We bring in simulation because experiments on a very small scale are much more expensive than on a macroscopic scale. So it is worth doing simulation there. And I just said molecular mechanics is used. That's typical sort of a name for a set of methods that just describe atoms as spheres connected by springs, and one can run simulations that way and understand how crystals behave and how molecules behave, large molecules. And then if you go down to the constituents of those things, what are molecules made of and crystals? They're made of atoms, and sometimes you want to include electrons. And the properties of those is mostly now established through simulation and some experiment. So you do experiments to typically validate the simulation model. And the field of study of that is quantum mechanics, and sometimes empirical models that are derived from that. If we go even further down on the atomic scale, then the components of an atom are electrons and nuclei, and those properties are established basically through simulation, almost entirely. And quantum mechanics is still the theory that we have, and that's what we use. If you want to go further down, there's a very big gap here, the subatomic scale, and that's the very big gap that was sort of apparent in that zooming movie. Then the components are the elementary particles of the standard model of physics. The properties are established by calculation, and some consequences are verified by experiment, and quantum field theory is used to describe these interactions. And if you want to go down even further, then there's something called a Planck scale, and the components are unknown, the properties are unknown, the laws are unknown, and we're not really going to talk about it. Why can we avoid talking about it? Well, it's again because of that big gap between the atoms and the nuclei. So all of chemistry and materials and higher length scale stuff can be understood based on the atomic nucleus as a point particle and the electrons. It doesn't mean that that's reality, but the next level down is 6 orders of magnitude. So it's actually a very, very good model. So let's take that point of view of taking electrons and atomic nuclei as our objects and calculate the world upwards from first principles. So the first guy who really thought that this was a good idea is Paul Dirac. And this is it's one of his, all his papers are famous, but it's one of his famous papers in 1929. If you look at this circled paragraph, it says that this was shortly a few years after the establishment of quantum mechanics. And he says that the underlying physical laws are known, and the whole of chemistry, and that underlies the whole of chemistry. And now the difficulty is that they're so complicated that no one can solve them. Exactly, right? So it therefore becomes desirable that approximate and practical methods of applying quantum mechanics should be developed, which can lead to an explanation of the features of complex atomic systems, i.e. calculating the world. And this, he didn't name it like this, but we could call this the Dirac program of creating these approximations. And we did pretty well in the last 100 years. So I'm going to show you some aspects of that, some trace along that route. So this was 29. So jump forward 35 years. And a key point was the introduction of density functional theory. It's a theory of an effective theory of quantum mechanics. it is much, much, much cheaper to carry out than the real thing, than what the original thing that Dirac came up with. It only needs the electron density, in principle. It doesn't need all that mucking about with wave functions. And so this was formulated in 1964. In 1985, the first realistic calculation took place on 8 atoms of silicon, so the unit cell of a silicon crystal by Carr and Parnello. And that was actually sort of the birth of a very large part of modern first principles simulation. And to give you an example, that's 12 years later, Partij and Schwenker calculated the properties of the water molecule much, much more accurately, in fact, than density functional theory itself would allow. And they calculated the vibrations of it, the vibrational modes. And if you look at the energy differences between different vibrational modes, that's where the water molecule will absorb or emit light, and that can be verified experimentally. And there is a very funny throwaway sentence in that paper where it talks about the matching of their calculation with experiment. And it says that some of the outliers where the match isn't right appear to be due to transcriptions error in the preparation of the experiment of the database. So the experimentalists just got the decimal point wrong when they were transcribing by hand the vibrational frequencies. So in this sense, we can say that calculation is better than experiment. The computer doesn't make an error. The reason they were able to say this is because the mismatch data points all were on the same physical page in a large table of numbers. So only on that page, everything was off by a factor of 10. So we have many, many other methods. Amongst them, density functional theory here, but quantum chemistry or quantum mechanics as Dirac would have liked it, or Dirac created it, is sort of down here. We can do a few atoms, let's say 0 error, but there is this whole hierarchy of approximate versions. And the stuff on the left is really quantum mechanics, and that's sort of the Dirac program. The stuff on the right, I put them there because that is how you get to 1 million atoms or 10 to the 8 atoms. That's empirical. So I've still included a bunch of empirical models, but really the Dirac program is going from left to right. Quantum mechanics is real. Let's investigate its consequences. So really density functional theory, if you look at the numbers here, 100 atoms and the picosecond, so that's 1,000 femtoseconds, and the femtosecond is a typical motion of atoms in a material or in a molecule. That's the time scale of motion. So we can do thousands of cycles of atoms vibrating, and we can do 100 atoms. Well, 100 atoms is a lot if you want to describe organic molecules, if you want to describe different kinds of crystals, then you can do a lot with 100 atoms. And that's why I sort of circled it. That's why it's been a sort of sweet spot in the last, let's say, 40 years in this program. So what sort of things can it do? So you can use it to calculate phase diagrams. So here's an example. This is the carbon phase diagram, but look at the axes. So they are pretty wild, right? So this goes up to 10,000 Kelvin and goes up to 2,000 GPa, gigapascals of pressure. So that's about 4 or 5 times the pressure that we have at the Earth's core. And you can definitely not do experiments. You cannot even do experiments at Earth's core conditions, and let alone at 6,000 degrees, because you have nothing to hold your experimental material in. But carbon and diamond will melt at a certain temperature and pressure, and diamond will in fact transform from the tetrahedral structure that you all know to a BC8 structure. It's a different crystal arrangement of the carbon atoms, and we can calculate what these phase boundaries are. And at the bottom end, we can even verify them with experiment. We can do aqueous, something completely different, aqueous solutions of many, many different ions. So these are polyatomic ions when you put them in water. And the structure around them and the water structure is very complicated. And that will affect how they pair up or not, how fast they diffuse, and so on. And if you want to understand that, you need simulation. Experiment is you can get some experimental evidence, but not of the detailed structure. So density functional theory gets it right. The evidence for that is this plot, which is the ionization potential for all these different ions as compared with the experiment, and we get that right. So there is a sense in which we trust this model to then tell us the things that experiment can't access. And the third very large area is surface, where DFT has been successful, density functional theory, is surface science. So lots and lots of things are happening at surfaces. Just think of catalysis or battery electrodes or the surface of a solar cell. Lots of interesting things happen there, full of defects. And you can do experiments in high vacuum, but you can't just, these are molecules. What you see here is STM experiment on a surface of titania, so titanium oxide. But you can't just make out the atoms. So that's, if you could see all the atoms, could see all the structure, it would be great. But experiment just cannot access where the atoms are, and that's why you need calculations. So if you do the calculations, you can, of course, place the atoms where you want in the computer, use density functional theory to try and understand how this molecule rotates and sits on this surface. And by doing a lot of work jointly with experimentalists, you can correlate that with what you see in experiment. These are examples. There are lots and lots of other properties. Okay, so material properties, thermal, dynamical stability, catalytic reactions, drug properties. I may say something about that if I have time at the end. Semiconductor defect properties. Again, there's 40 years of evidence that we can compute those very well. So here's an example. I want to show you an example of what could we do with density functional theory. And I picked one of my very old studies 20 years ago. Here's a bunch of nanotubes. 20 years ago, everyone was super excited about nanotubes. It was the graphene of the age. It's just graphene rolled up, or as they said later, graphene is unrolled nanotubes. So this is an example, or this is an image. But what we were trying to think about is how these things are grown. So typically, in these early days, they were grown by a molten metal particle. So you take a piece of metal nanocluster, like that iron works pretty well, or nickel, and you rain down carbon on it, either just a carbon-containing compound, or in fact plasma, so ionized, just the carbon atom itself. And when you do that, a nanotube grows out of this. The particle is at the end, and you can see the experimental image here. The nanotube is typically a multi-volt nanotube, and it kind of exudes from the end of this particle. And the typical idea of how this happens is that the carbon dissolves into the metal, forms a eutectic solution, and when it's supersaturated, it comes out at the other end and naturally forms these nanotube structures. And this is an Arrhenius diagram. So this is inverse temperature here, and the growth rate that you measure experimentally vertically. And this line, this dotted line, is what you get if you rain down these hydrocarbons, if you put hydrocarbons into the system. And it's a very steep line. So that means that the energy barrier, the activation energy of this process is very high. But people actually here in Cambridge figured out that if you put, not just put the hydrocarbon in, but you put plasma onto this, so plasma-enhanced vapor deposition, you first strip all the hydrogens away from the carbon, you get a growth rate that has a much, much shallower slope. And you can do this on nickel, you can do this on iron, you can do this on cobalt, and instead of this 1.21 electron volt barrier, so activation energy, you get activation energies that are between 0.2 and 0.4 electron volts. So much, much, much lower. And it's sort of not clear what is the mechanism, how is the mechanism changing. So modeling comes to the rescue. And this is sort of that's why I have it here. It's an illustration of the very tight coupling of modeling and experiment. To do all these calculations, I'm showing you this is the surface of a metal, and these are various example configurations of carbon and hydrogen, and we are computing energies and barriers, so reaction barriers, which would then be thought of as the activation energies. And the growth, once you have a carbon atom on the surface and you have some hexagons already, the addition of the carbon to the hexagon is basically barrierless. That's not limiting any of the rate. That's very fast. The decomposition, however, of hydrocarbons on the surface has a high barrier according to these calculations. 1.4 eV for this situation. If you decompose on a step edge, which is quite likely that this particle is not a flat surface, but it has various edges and corners and so on, and it's not hard to intuit that actually those might lead to a lower barrier for these reactions. Actually, it is lower, but not that much lower. We got 1.3 for this nickel step edge. If you think about bulk diffusion, the diffusion of carbon through this metal, which is necessary for the established mechanism of this kind of growth, that's about 1 eV. So again, at these very low temperatures, remember, this is 1 over the temperature, so 1 over K. So here you're down to 2.5, right? So you're down to 400 K, nearly room temperature growth. You cannot have this rate of growth with a 1 eV barrier. It would just be too slow. So the last option is surface diffusion. So it's the surface diffusion barrier of the carbon just hopping along the surface is 0.4 eV. Okay, so this is a consistent picture of what's happening. It's a change of mechanism that is, you no longer have dissolution of carbon inside the metal that happens at high temperature, but you have surface hopping, and that can only happen if the carbon arrives without the hydrogen, because removing the hydrogen is way too slow. Okay, so this all took about 2 years of my life to do those calculations. DFT is good, but it's slow. It's very expensive computationally. Okay, so, and you can see that we didn't model the nanotube growth in the computer. I didn't have ever a nanotube in the computer. I didn't have a metal particle. I had these very, very small model systems, these, 60 atoms of metal, a couple of atoms of carbon, very carefully placing them and computing their energies and barriers. So sort of a very painstaking manual deconstruction of what the experimentalists would see. So, okay, let's just jump forward 20 years. Computers are getting faster. So what are the sort of things that we can do with DFT today? And it is very exciting. With more compute, we can do more. So, for example, people are searching for high-temperature superconductors. There is an evolution of the record temperature in superconductivity by year, and you can see that there was some sort of steady increase. This is all experimental data that you're seeing here. You can see a steady increase here up to the 1990, and then there's a very big change in slope. People are starting to discover high-temperature superconductors. And this is room temperature, so that's the holy grail, right? And there are materials now that are nearly room temperature. The one snag is that they're very high pressure. But that is still, although that limits the practical use of these particular materials, it's still a fantastic advance because this demonstrates that temperature on its own doesn't kill superconductivity. You can go to temperatures as high as 250 Kelvin, right? So now there is an arrangement of atoms which leads to superconductivity at nearly room temperature. At the moment, these materials need a high pressure to keep that arrangement of atoms. The search is on for materials that can keep that arrangement without external pressure. But the reason I brought this whole thing up is because these materials were actually predicted by computation. No experimentalist was browsing through all the available materials and testing them painstakingly one at a time. Calculation was used to search for potential high-temperature superconductors. They were predicted, and then people went to the lab. So this is really, instead of what I did 20 years ago, experiment comes first with a puzzle, and then we do a few calculations to try and kind of resolve the experimental conundrums to get understanding. This is now real predictive calculation. This is what maybe Dirac was dreaming of. And the reason we can do this for small crystals and not for much bigger things is computational cost. So even back then, 20 years ago, I was frustrated by how expensive this thing is. So let me just give you some numbers for that. So this kind of DFT that I used for the surface diffusion of carbon, or that's used to predict superconductivity, for 100 atoms, you take one compute node, like one we have here in Cambridge in the CSD3, and it takes about 1 hour to get the energy of a single structure. And the scaling is cubic, so if you want 1,000 atoms, that's 10 times more atoms, 1,000 times more expensive. So that's 1,000 hours. You better only do it if you really, really want the answer. If you want a better level of DFT has different versions, different scalings, better accuracy, but that costs more. So 20 times a prefactor and scales now as n to the fourth. So it would cost you 200,000 hours to do the 1,000 atom calculation. Not that you can do it because you'd run out of memory. I just plugged in the number into the n to the 4, but if you could do it, that's what it would cost. And even that DFT is doesn't have the ultimate accuracy. Coupled cluster theory, a version of quantum chemistry, is really, really, really very accurate for almost everything, but it scales as n to the 7. So again, you would never actually be able to start this calculation. You would run out of memory. But 10 million hours for a single energy of 1,000 atoms. So people don't do that. People stick with the normal DFT at 100 atoms, and yet we spend almost all the time, about half the time, but almost all the time in atomistic simulation using DFT to compute materials. This is the usage graph of the largest computer that's in the UK available for academic work. And this graph is from 2021. And this code, VASP, takes about 35% of the entire machine all the time. And that's because it's doing density functional theory, typically molecular dynamics. So what is that? In molecular dynamics, you don't just compute energies, you compute energies, forces, and you actually follow the trajectories of atoms in what they do. So you have atomic positions, you solve the Schrödinger equation in, for example, this density functional theory approximation, and then you get forces on every nucleus, every atom, and you simply plug them into Newton's law. That's very well established, how you integrate Newton's law in time if you have those forces available. But it's very, very wasteful. Not only is it very expensive, but you actually, at each time step, you throw away all that juicy quantum mechanics that you computed, and you just retain the forces. And then you go round and round again in this loop. So the idea is very natural, that what you really want to do is not do that at all, but just go from the positions directly to the forces. We need to develop a method, a formula that gives us the force given the positions without conjuring up quantum wave functions, electrons, and so on. I don't care about the electrons at this point. I just want to follow the trajectory of the atoms. And it's a map. It's a function from r to the 3n. So the 3n xyz is 3 and times n atoms, that's 3n. This is the positions of all the atoms in my system, and that's mapped to the single real number that is the energy. Quantum chemists have been doing this idea for a long time, but only for very, very small molecules. All the methods of doing this that are established don't scale for large n. They scale worse than coupled cluster. They scale exponentially. So the real question that we asked 20 years ago is, can we do this in general, not just for molecules, but also materials and for very large systems? And we want to do things like this. This is one of my favorite molecules. It's called SNOP. It's sulfur, nitrogen, oxygen, phosphorus. And if you decorate it with various number of hydrogens, it does different things and actually rearrange it in its order. And its quantum chemistry, its electronic structure is horrendously complicated. And here's another thing that we want to do, battery. Here's a baby battery. It's not a realistic simulation of a real battery, but it has components of electrodes, and here's a graphite anode, and here's a nickel manganese oxide cathode, and there's some electrolyte with lithium, and we want to do these kinds of simulations. And density functional theory is far, far too slow to do anything like this. So what we really want to do, and this is what I call first principles force fields, is to do some density functional theory calculations, small ones, maybe 100 atoms. I can do that in 1 hour. We can do thousands of those. And those give us sample points on the potential energy surface. This function that maps positions to forces, positions to energy, and then the gradient of the energy is the force. These are valid samples on that high-dimensional function. And what we want to do is fit it. Make a model that interpolates between these points. We do that by representing the atoms somehow. Here's an atom. It has neighbors at certain distances. Fine. That's going to be my input. And I want a function that tells me what the energy of that atom is, and consequently what the forces are. And I don't know what that formula would look like, so we need to do some regression. We need to allow ourselves some freedom. It's like function fitting. And we have a lot of data, and we can fit a function that does the job of what the quantum mechanics does by very, very expensive computation. We want to do that quickly. So it's about function fitting, and you've all done it. You've all done simple versions of it, right? Here's a function in 1D. Here are some data points, and let's make an interpolant. Okay, so I have some basis function. Here it's a Gaussian. Here's my little basis function. And I can represent this y as a sum of Gaussians. So k is my Gaussian, c is a coefficient. Let's take a linear sum. And the c, k is all fixed, and the c is arbitrary. Let's fit it. Let's get a set of c's that fit the function. And what you get are a really good fit where you have data, like here and here, and a really bad fit here where I didn't have any data. Okay, that's normal, so we just need to collect a lot of data. And there's a lot of detail in how this works. So if you change the width of the Gaussian, your fit will look better or worse. Here's a fit with really, really narrow Gaussians. Terrible. It still fits all the points, but in between, it's really bad. Here's a fit with, appropriate length Gaussians. Here's a fit which not only fits the function value, but fits the derivative. If you only fit the derivative, that's a terrible idea. Here's a function which has all the right derivatives, but the wrong value. And if you have an appropriate length sigma and you put in energies and forces, so values and derivatives, you can get really good fits. So a very brief history. This is called machine learning when you do it in high dimensions. So a very brief graphical history. Imagine that this is the potential energy surface. And if your molecule is very simple, it really is one-dimensional. If I have O2, then it just does this. That's it. The only descriptor is the distance between the oxygens. I can take data and fit a function. But 2007 was where this field really took off, when people figured out how to do high-dimensional fits, how to do this in not one dimension, but 100 dimensions. It's all the neighborhood of an atom is taken into account. And by the end, maybe in 20 minutes, I will get to the extreme generalization, the wide transferability, where you take data only in one part of configuration space, one kind of system, and you get a model that's reasonably good kind of everywhere, which is typically not what machine learning models do. If you go very far away from training, they do nonsense. But here we find they don't. So function fitting in high dimensions is essentially what machine learning is. And that's what we do to quantum mechanics. So there are challenges that are a bit different from traditional machine learning that you might find in speech recognition or face recognition. When we want to do molecular dynamics with the fitted model, so the simulation is what is called autoregressive. I make one step based on my model. It might be a little bit wrong. I do a next step. Again, it's a little bit wrong, but it's based on something that's already a little bit wrong. And I do the next step, and I do the next step. So errors compound during the simulation. And we want to do millions of steps in the simulation. So each error needs to be very, very, very small in order for this to make sense. And the required accuracy, basically, on the energies of molecules and materials is about 99.99% of their binding energy. So extreme accuracy. Compare that to useful accuracy of face recognition. If you make an error 1 in 100 times, that's great. We can go on the UK border, have those machines. They make errors, especially if they know one can kind of get an assessment of how big the error is, and you only need one guy in the booth handling 20 machines, right? Because the machines are more or less almost always right, but 1 out of 100 they're unsure, fine. Then the guy looks at it. Okay, so it's a huge benefit, and you see them in real life. 1 in 100 accuracy of 1% is fantastic. Well, not here, because errors of 1% would compound extremely quickly. Okay, so here's an example from 2020. So we started this in around 2005. 15 years later, we've learned how to do this well. So we collected all the carbon structures that we can find on the internet, and we generated a few ourselves, and computed them with density functional theory. So 9,000 basis functions were used, 6,000 DFT evaluations. So that's the 6,000 hours of compute time. And we get a model where the target, what I'm showing you here as results are defect formation energies. So what is the energy of adding a carbon, extra carbon to diamond? What is the energy of removing a carbon from perfect diamond? What's the energy of taking a graphene sheet and rotating one of the bonds by 90 degrees, right? These are all defects, changes to the basic structure. And we want to get those energies right. And we get them right, basically. The previous empirical models are the sort of crosses, and they're kind of all over the place. And so we can get models that actually do the right thing and give us about a 1,000,000-fold speed up over doing that with the explicit quantum mechanics. So this kind of works. It's still a lot of work to build up such a database and a lot of upfront cost, but this idea kind of has legs. It's actually working. Let me show you a realistic application. So this is not done in my group, done by Volker Deringer. He was here actually before. He now is professor in Oxford. He was a fellow in my group. So the application here is GST, so germanium antimony telluride, which is a phase change material. It can either be crystalline or amorphous, and it's easy to go between the two. Here's the device. So you have these crossed electrodes, and between every pair of electrodes, there is a piece of this material, about 500,000 atoms worth. So this is a nanoscale system. And by selecting the two electrodes and applying a voltage, you can pass a current through the device and apply heat, essentially just Joule heating. And depending on how you apply that heat, you can either apply a lot of heat or a little bit of heat for a longer time. You can either amorphize the material if it was crystalline, or crystallize it when it was amorphous. And the amorphous and crystalline versions have different electrical conductivity. So it's like can serve as a switchable memory. And this is a small scale MD of molecular dynamics showing that if you do it at great expense with DFT, with explicit quantum mechanics, you get the same kind of recrystallization behavior. Here the red is amorphous, the yellow is crystalline. And the machine learning model that they fitted kind of shows the same dynamics and the same behavior. So then they can go ahead and simulate what happens to the real device. 500,000 atoms, where you would never be able to explicit quantum mechanics. You pass the current and it does the right thing. So since then, they've taken this further and simulated real devices. So this is an 800K atom simulation of the real device geometry, which is shaped like this, with this piece of material in between these two electrodes. And when you pass the current from the bottom, in this case, you pass them through this small wire here, and these are called mushroom topology devices. And what they're showing in this paper is that depending on the amount of current that you pass, you can actually crystallize and amorphize different amounts of this material. So you can store more than 1 bit, because the electrical conductivity will depend on the amount of crystalline and the amount of amorphous material. Okay, so now I will have a short geometric interlude for about 5 minutes. I want to show you a small problem that is independent of everything else that I've talked about, but it was actually at the crux of how to make progress with these models. So it's about what would be a good descriptor for an atomic environment or a molecule. How do you take atomic positions and how do you plug them into a neural network or any kind of regression scheme, a function fitting scheme that would then give a good model? So you want some properties of this description. So you want this description to be invariant to basic symmetries of physics. rotation, translation, permutation. If I rotate my whole molecule, it shouldn't change its energy. If I move the molecule over here, it should still have the same energy. And if I permute the atoms, if I tell you about which carbon is where in different order, it shouldn't matter. The descriptor needs to be unique. So if I describe a molecule with a certain number of certain descriptors, I don't want two different molecules to have the same descriptor, because my model will give you an energy based on the descriptor, and if the molecules are different, I want to have different energies. I want a smooth descriptor, something that is continuous, that if I bring an atom from far away and now it's part of the molecule, there's no point in which there is some discontinuity, some kind of jump in how I describe the system. And I want something that's systematically improvable. The whole point is that we can add more data, get more accuracy until we have a model that we like. So it turned out that satisfying these requirements is a very deep mathematical problem that wasn't solved. So let me illustrate how this works. Let's suppose that descriptors are the distances between atoms. That sounds really good, right? If I know all the distances, I can sort of think about what the energy of that molecule is. So here are some distances, and if you can assemble them into a tetrahedron. That's great. And I have one of these things here. I'm going to pass them around. Be gentle with them. They might fall apart. So the question is, I have two of these here, and so you can pass them around. They have the same distances. They have the same rods, but they actually are different. So that means that, you can pass them, pass them pairwise, so that you can see that they are the same distances, but they are different tetrahedra. You cannot rotate one or the other. You can't permute one into the other. Okay, so that means that descriptors, distances, are rotationally invariant. Great. If I rotate the system, their distances don't change. If I translate the system, the distances don't change. But they're not unique. If I can have the same set of distances, but I can get two different. Imagine that these are the neighbors of an atom. The neighborhood will be different. Or if this was a molecule, there are molecules that are like tetrahedra. Imagine the hydrogen atoms around the carbon, methane. At some higher temperature, the hydrogens would be the corners of a tetrahedron. So how do we solve that? Well, one obvious potential solution, is to not just think about distances. What if I think about the angles, right? Because that's what you see in this, that the angles are different. And so we can just generalize that and think about the triangles. Okay, so if I take each of the triangles out of one of these tetrahedra, then those triangles are not present in the other one, right? So the list of distances and list of all the triangles that I have do satisfy the requirements. They are rotationally invariant. The list itself is permutationally invariant. I don't care which triangle is where. And at least these things, with distances are not unique, the triangles are. So here's another example, and this is from the paper where we thought about this. Imagine that we have the central atom, we have some neighbors, 1, 2, and 3, and either 4 or 4 prime. And it turns out that the distances are all the same. It's the same thing that what you're holding in your hands. What I'm showing you here is the angular distance. So the distance around the circle, right? It's the same as, effectively, the same information as the Cartesian distance. And the list of distances are the same between 1, 2, 3, and 4 on the one hand, and 1, 2, 3, and 4 prime on the other hand, but they're just swapped in order. Different ones are connected by those different distances. So if I just give you the list of these, 15 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers, you don't know which one I'm talking about, 1, 2, 3, 4, or 1, 2, 3, 4 prime. Right? So the statement is that the full set of distances, or triangles with the central vertex, so because the distance between two atoms is the same as the angle at the origin, do not determine the structure uniquely. And the very, very surprising thing is that if you go one above, so the triangles, which do solve this particular problem that you're holding in your hand, they are also incomplete. Now, this is a horribly complicated diagram. But I have a prop here. So this is, I can also pass these around. So these are a set of 7 atoms, and all the triangles between the 7 atoms are the same between those 2 cubes, and yet you will not be able to rotate one into the other. So that's really surprising, and that's a new result. So, and that's bizarre. I've colored the triangles in there, so every color you can check if you want that every color in one colored triangle appears exactly in the other cube as well as a same geometry triangle. But the 2 set of atoms are not the same. So the full set of triangles with tetrahedra with a vertex at the origin do not determine the structure uniquely. And people have been using these kinds of descriptors for years. So have I, because this result is from 2021. Okay, so that's the interlude. This was an unsolved problem until recently. There is a solution. They are called graph network models. So we take the neighborhood of an atom, we compute the 4-body, some kind of 4-body local descriptor. So for example, all the tetrahedra with the vertex at the center. But then we don't stop there. We take those descriptors and we pass them around. Each atom passes that list of the tetrahedra that it is part of to the neighboring atoms. And those neighboring atoms form tetrahedra from that information. I'm describing it to you at a high level. These have equations. I have them so small that I'm not tempted to talk about them in detail, but you can read them in the paper. It's called the Mace model. And that solves the problem. And in fact, it turns out, we've understood eventually, that this same basic idea is the foundation of lots of people's solutions that actually do work very well. But we understood why. And it turns out that mathematicians have now proven that this construction mathematically is rigorous. So it does give a unique representation of the entire structure. Okay, so now let's see if we can do extreme generalization. So we have a new model made a couple of years ago that's based on this construction. And let's try to fit not just GST, germanium antimony telluride, or carbon, but let's try to fit all materials. Let's have a model for quantum mechanics. So where's the data going to come from? Well, it turns out data already exists. So there's something called the Materials Project, which collected huge numbers of already made DFT calculations. People have done it for various purposes. They recomputed it all with the same consistent settings of the software that does the computation. And they store it, and you can download it. So there are many, many structures, over 1 million structures in here that have been computed with density functional theory. And so we have a model that's trained on all of this. It covers 89 elements, basically not the really badly radioactive ones. And it's all crystals. So this is sort of a little movie just to give you an idea of what's in the database. These are all inorganic crystals, right? It's not all of life. It doesn't have organic systems. It doesn't have porous materials, but it doesn't have amorphous materials. But it has all crystalline materials that are known to humankind. And when we fit to that, here's a little benchmark from November 23. Now, what the benchmark is trying to, and our model is at the very top that month, that stayed like that for like 3 months. And then people started jumping on this, and there are now much, much better models using similar principles. But what this benchmark is trying to predict is, if I give you a new hypothetical material, maybe it's going to be the next superconductor, what is its energy going to be? Is it a stable material? That's what the benchmark measures. And so the number, this F1 score is high if you are predicting a held out test set to be of the correct stability. So there was this set off a huge flurry of activity. But what was even more surprising is that if you take this model, not only can you predict energies of small inorganic crystals, which was sort of nice, but you can actually do all of chemistry. Now that was completely unexpected. what happened is that people started, my students in my group started doing molecular dynamics with this model fitted on small inorganic crystals. But they started doing it MD on amorphous carbon and battery anode and water and hydrogen combustion. It all kind of worked. And that's really weird. We didn't believe it for weeks. Here's sort of what happens. You run MD and it's all kind of stable, it's chemically sensible, the right kind of things happen. For every material, it's qualitatively right. For many materials, it's quantitatively right. You can actually do the modeling science that you want to do. Here's an example where it's qualitatively right. So hydrogen combustion, you'd start off with just hydrogen molecules and oxygen molecules, you let it go, and you get the burning of hydrogen, water, but also all the correct intermediates, including ozone and hydrogen peroxide. None of that is in the training database. The training database is inorganic crystals. There's 8 structures of ice at 0 temperature, and that's it. Whereas here you're getting chemical reactions essentially correctly. Here's another quantitatively correct thing, and it's so very topical because of the Nobel Prize was just given a week ago for MOFs, metal-organic frameworks. Again, not in the database. These are very porous materials that can be made on a large scale, and there are many applications, but one of them is gas storage. So here's a little carbon dioxide molecule, and it's being investigated in this structure of, it's called MOF74. It's one of these metal-organic frameworks. So what we can do, because the model is fast, is run 1 million steps and ask where is that carbon dioxide going to be and what is its free energy? How likely is it to bind to this structure? And when you do that with this foundation model, the model trained on small inorganic crystals, you get this kind of answer. And it's very similar to the answer you get if you train one of these ML, machine learned potentials, to that the exact system. So generating painstakingly all the quantum mechanical data for that particular system, taking many tens of thousands of hours, and then you run the MD, you get a very similar answer. And this is what you would get from a simple empirical model that people have had on the shelf before. And once you don't need to train, this model is just off the shelf, you can swap out the metal ion. You can take Mg and manganese and iron and cobalt and all these, and you can change the linker, the organic linker. That's the structure of these MOFs, with metal ion at the corners and organic linkers. And now you can study the binding landscape of carbon dioxide for all of these systems, kind of without doing any extra work. So really what we've done is managed to take these kinds of models with these kinds of accuracy and applicability. The foundation model kind of brings them over here, so we can do simulations of many tens of thousands, maybe even 1 million atoms if you have a big enough computer. And with a little bit of fine-tuning, by a little few extra configurations, you can make them as accurate as the original quantum mechanics. So, this is one of my favorite pictures. It's the periodic table made out of atoms, right? And you can just let go, and you can see what happens. The force fields exist for all of the periodic table. It's thousands to millions of atoms, tens of nanoseconds can be simulated, so many millions of steps. And it's basically with the quantum mechanical accuracy that was used for the last 40 years very, very, very successfully. So large data was needed, but really it was about diversity rather than the size. We can now do it with smaller data. And we're really interested in testing the use cases now, rather than just how accurate it is. Really seeing how it can be used in all the different fields. And I have some future stuff. We still need to put in a bit of long-range electrostatics. Those are very weak interactions that in some systems matter, and we don't have them yet. And actually, we are hitting the problem of, is the electronic structure good enough? Is the level of quantum mechanics that we are using, we can